Howdy everyone, welcome to the Chapter 6 tutorial video where we'll look at some example problems on molar conversions using formulas as a conversion and then determining an empirical formula from some data. So some common example or common types of problems you'll get in Chapter 6 both on homework and the test. So let's hop to it. Oops. There we go. Alright, first off, molar conversions. This is the backbone, right? This is how we go to moles or from moles to a variety of other things. So if we look here, we have two rows. We've got water and we've got sulfur dioxide. We've got columns for mass, moles, and molecules. So we want to do conversions between them. So when we, first off, to go between mass and moles, we always need the molar mass. And so that we need to look up numbers off the periodic table, add them up. And so I'd like to do that ahead of time, just say, okay, I know what the number is, so when I need it, I can just plug it right in. So for water, we add up two hydrogens, 1.01 each, oxygen 16.00, so we add that up, and that is 18.02 grams per mole, so we've got that number handy. For sulfur, that's 32.07, each oxygen 16, when we add that all up, 64.07 grams per mole. So we've got those two numbers for when we need them. All right, so for water, this one, we can go from mass to moles to the molecules. And actually here above the table, let me just remind ourselves how we do that. This is molar mass that will go between these two, assuming it's grams. So if you notice, we got a kilograms here. We'll have to fix that. And then from moles to molecules, that's where we use Avogadro's number, the 6.022 times 10 to the 23rd. So for water, we just go in the one direction. For sulfur dioxide, we'll have to do one this way and one that way. That's okay. All right, so first off, with the water, because that's kilograms, we've got to convert that. That's going to be 112,000 grams, right? Because kilo is worth 1,000. So rather large number we're working with here. But let's start with the water. So 112,000 grams of water. And then it'll be, well, grams goes on the bottom to cancel out. Moles of water goes on top. 1 mole is 18.02. So, right, since we already had that number, I can just plug it right in. And that'll give us our first answer. So 112,000 divided by 18.02, it's 6,215 moles. With rounding, that would be 220 moles, or you could write 6.22 times 10 to the third moles, but yeah, that'll, moles, don't forget our unit. But yeah, it's a large number, makes sense. So yeah, I'll just make it 6.22 times 10 to the third. So that's our first answer there. Now for number of molecules, we'll use Avogadro's number. So I'm just going to leave that right in there and say, okay, well, in 1 mole of water, or any substance, it's 6.022 times 10 to the 23rd molecules. And so we'll take that number and times 6.022 and all that. Let's see. That'll add one. I'm not using a scientific calculator, which is a problem. But I believe this should be 3.74. And then that'll be 26 times 10 to the 27th. If I'm doing math, because 3 and 23 is to the 26th power. 6 times 6 is 36, so that's where we're getting the 37. But that'll add one more power. So yeah, to the 27th power of molecules. So that'll be our answer there. 3.74 times 10 to the 27th. And that makes sense, because right, if 1 mole is 10 to the 23rd, well then thousands of moles will be even more. Or 3 to 4 powers more. So yeah, that checks out. Also, please use a scientific calculator. I just found myself without one at home somehow, and so I'm making do. Also, good to know your exponent rules from math class. All right, now for the SO2. Here we're not going to do a two-step because we're starting with moles. So we're just going to go one step to mass, one step to molecules, just one problem each. So let's draw a little line here and work on the sulfur dioxide. So I'll do the mass first, going to grams. So we have 2.44 moles of SO2, and then moles of SO2 on the bottom, grams of SO2 on top, and so yep, 1 mole is 64.07 because we already have that. So yeah, just 2.44 times 64.07. That will give us 156. It's 0.33, but with 3 sig figs, 156 grams of SO2. So I can write that in, 156 grams. And then for the next calculation, again, just starting at moles, going to molecules. So 2.44 moles of SO2, and then 1 mole of SO2 on the bottom, 6.022 times 10 to the 23rd molecules of SO2 on top. And so 2.44 times 6.022, and then it's times to the 23rd, so that would be 1.47 times 10 to the 24th molecules of SO2, and that makes sense. 1.47 times 10 to the 24th. All right, so that's how you do those problems. So it might be a two-step problem, might be one step, multiple times. Technically, this was like multiple one steps. We just because we had to get that answer in the middle there for moles, but it all checks out. Just make sure you're keeping track of which relationship am I using. Grams and moles, use your molar mass. Molecules and moles, use Avogadro's number, or even particles and moles, Avogadro's number. And then just watch out. The book does love to throw in some lines that either have kilograms or milligrams in them. So make sure before you use molar mass, you're in grams. All right? The next problem then, 6.61. How do we use formulas as conversion factors? Because this one, it to me, it always seems easy, but sometimes then I forget to, not teach it, but, point out specifics about it, and then I noticed people have trouble with it. So I'm trying to make sure I point this one out. So for these problems, technically the problem was just which one has the most moles of oxygen. So I've changed this problem slightly to be how many are in each, so that we definitely know which one has the most. So the key here is we say how many O's are there per formula, but then start with the given. So for this case, when we have 2.3 moles of water, well, if we multiply that in 1 mole of water, based on that formula, there's 1 O. So there's 1 mole of O. And so 2.3 times 1, there's 2.3 moles of oxygen. All right, and then let's change colors so that these don't all bleed into each other terribly. All right, let's go to slightly lighter blue. All right, now for this next one. All right, we say, okay, now it's 1 mole of hydrogen peroxide. And in that, well, there's 2 O's, so there's 2 moles of oxygen in that one. So 1.2 times 2, well, this one's got slightly more, 2.4 moles of oxygen. All right, now we go, and we'll change colors again. Here's a nice, what's that? What was that? Oh. Let's go to this purple color. All right, so we got 0.9 moles. All right, so again, 1 mole of, in this case, sodium nitrate. Well, hey, there's 3 O's in that that formula, so it's 3 moles of oxygen. So 0.9 times 3, slightly higher still, 2.7 moles of oxygen. And then in part D, let's go to green. I'll write it down here slightly. Hopefully that's visible. In this case, 1 mole of calcium nitrate. Well, that's 3, but then times 2, there are 6 moles of oxygen. So 0.5 times 6, slightly higher still, 3.0 moles of oxygen. So the original question is which one has the most moles of oxygen? It would be letter D. Oops. Because 3.0 is greater than all the others. But that's the key. If you ever need to go, for whatever reason, between the entire molecule and just part of the molecule, you use the formula. How many of that element are in that formula? And it's a mole to mole ratio. 1 to 1, 2 to 1, 3 to 1, 6 to 1. All right, so that's how we do that one. All right, next up, empirical formulas. How do we get this to say we got some lab data? How do we turn that into a formula we can use? And so we've got this. I'll just underline the key information. It's 1.78 grams of nitrogen, 4.05 grams of oxygen. That's it. Nice, only 2 elements. Calculate the formula. So step 1 was always take the grams or percent abundance of each element and turn it into grams, but take the grams, make it into moles. So we'll do that for nitrogen. 1.78 grams of nitrogen, and we turn that into moles with the molar mass, and that number on the table, 14.01 grams of nitrogen. And so we'll just do that division real quick. 1.78 divided by 14.01, and we get 0.1271 moles. I'm not going to care about sig figs. It's just, yeah, it'll round out itself. It'll be fine. And then we'll do the same thing to oxygen. So 4.05 grams of oxygen. We look up its number on the periodic table. It happens to be 16.00 grams of oxygen. So 4.05, divide it by 16, and we get 0.2531 moles of oxygen. All right, so that's step 1, turn the grams into moles. Step 2 is we want to get our ratio. We need, is it 1 to 1, 2 to 1, 3 to 1? We need the 1, so we find the smaller number of moles and divide by that. So in this case, the smaller number of moles is the nitrogen. So we'll divide both by 0.1271, 0.1271. All right. So this will be 1 nitrogen. And this looks to be about 2, but I'll do the division just to double check. Divided by 0.1271. Yeah, it's 1.99. 1.99 is 2. So that's 2 O's. So we have this. And then the third step is if we don't have whole numbers, we'll multiply everything by some common number to get whole numbers. We have whole numbers. We have 1 and 2. So I'll just put these together, and our empirical formula is NO2. Now, is that the real compound? Maybe there is a NO2 compound, but maybe there's N2O4, N3O6, N408. We don't know. We'd need extra information to find that out. There is a problem like that in the problem set, but for those, the book gives you the empirical formula to start with. So there you're just saying, okay, is the molar mass the same? Well, then the formula is the same. If the molar mass is double, then I've got to double this formula. If it's triple, I got to triple that formula. But that's the other problem. This is the tricky part, getting the empirical formula. Once you have that, then you can figure out the rest pretty easily. All right, so as always, I hope this was helpful. If you have questions, come in for office hours, go in for tutoring, email questions, but please get the help you need, especially as we start moving into some more math-focused chapters. If you say, like, I'm a little weaker on math, I'm not too sure about this, get the help. Come in for practice, even if it's just, I would like to do the homework while sitting nearby you or the tutor, whatever. That's perfect. Do that so that whenever you get stuck, you don't get stuck for long. You can say, here's where I'm at. Is this right? If not, please help me get back on track. All right, thank you very much. Have a wonderful day, and I'll see you back for Chapter 7.